Hello, welcome to video 28 in the lecture Advanced Mathematic Modeling. Today I want to analyze some results of a simple random walk, and I want to look at a simple, again, IID random walk, so independent increments, but what's happening if the random walk is biased. And what does this mean for our mean squared deviations? And so we want to use it as an example to see how we can calculate all these properties. Okay, and we assume again the simplest case. We have a Bernoulli trial, so we have increment. So let's write it again. Repeated but biased Bernoulli trial. So this means we have increments which are either +1 or the increments can be -1. So we jump to the right with a certain probability q, and we jump to the left with the probability 1 minus q. And now this q is not necessarily 1/2. So we have a biased random walk. Now the question, so what are the properties of the walk? And you remember from our calculation, now we want to know the properties of the walk, like the mean position or the second moments. In order to do this, we need to know the expectations first of our increments. So let's have a look. So what is the expectation value of our increments? And so, like, how do we do this? So we go with probability q, we go to the right, so we have q times 1, and with probability 1 minus q, we go to the left, so we have an increment of -1, and then we have the expectation of our increments, and this is 2q minus 1. And from this we see, we can make a plot where we have our parameter q, which goes from 0 to 1, and then we want to know what is the expectation of the increments. And so we have this function, it's a function which goes here to 0, this function. So at 1.2, if q is 0.5, yeah, then the expectation of the increments is 0, because this would be an unbiased random walk. But if the q is 1, then we go only to the right, then the mean value of the increments is always 1. If q is 0, then we go, q is 0, then we always go to the left, and our expectation is -1. Yeah? So you see, by this parameter q, we can shift from a walk where we only go to the left to an unbiased random walk towards a walk where we only go to the right. So we have here a parameter where we can tune the bias of our walker. So what is the expectation of e squared, the second moment? Since we now take the squared, so the negative sign goes away. So you see the second moment is just 1. So second moment is 1. What about the variance of our increments? So the variance of the increments is the second moment minus the first moment squared, and this is 1 minus this combination 2q minus 1 squared, which you can also write as 4q times 1 minus q. So you see the variance of the walk is a quadratic function of the parameter q. So if we plot the variance of our increments, so this is a quadratic function. And why this? I mean, like the highest variance we have for unbiased random walk, where we can go up and left, right and left. But if q equals 1 and we go only to the right, of course there is no variance left. And when we go always to the left, there's also no variance left. So we have basically here then ballistic motions where we just go in a straight line. There's no variance. And the largest variance we have for the unbiased random walk. Okay, so now we have most things what we need for our formula. We have the expectation, we have the second moment, we have also the variance. What about here this covariance function? This we also need. Let's calculate this. So what is the expectation of EI times EJ? And when I write it like this here, I assume always now I is not equal j. So we have different time points. And now you see there is several combinations. So we can either have both increments equal to +1. So this gives 1 with the probability q squared, because both increments are +1. We have also the option that both are negative, and we have -1 squared with probability 1 minus q squared, because both probabilities both are negative. We have 1 minus q squared, and then we have the chance that one increment is positive, the other is negative. So this is 2 times 1 times -1 times q times 1 minus q. So that's all 4 possible cases. And when you work this out and you calculate this, the sum here, so you see that's 2q minus 1 squared. And that's this expectation. But so what was the covariance? The autocovariance function EI times EJ if I is not equal j. So that's the expectation of EI times EJ minus the expectation of EI times expectation of EJ. And so we have here, we have this here, 2q minus 1 squared minus the expectation of the increments is 2q minus 1, which we have to square. And so we see the outer covariance function is always 0 if I is not equal j. So we see really, okay, that's we know the outer covariance function as a function of I minus j is the variance, is this value if I equals j, and is 0 if there is a finite time difference. So that was the outer covariance function, because we have an IID process, and so we have no memory. So in such a way, now we were able to calculate all the properties that we need, the moments of the increments, the variance of the increments, and these expectations and the covariance. Okay, so now we can, once we have this, now we can look what does our walker do. So let's see what is the expectation of the position. So the expectation of our random walk is as a function of time n times the mean value. So we find that the position of our walker as a function of time equals, so the mean value 2q minus 1 equals 2q minus 1 times the time n. And from this we see, of course, that let me do this plot of our walker here. That's time n, that's our walker, and so we see we have here a bias. And this bias goes here with this formula. For every q from this formula here, from this expectation, we see the bias. This would, for example, be an example where the bias is positive, and then our walks are random, but they scatter around this bias. So now what can we calculate next? Well, we can see what is the second moment of our walker. Then we need this formula, so n times the second moment of the increments plus this correlation sum. So let's see, what is the second moment as a function of time? So this is, let's look again, n times the second moment, but the second moment is 1. So it goes just with n times 1 plus, now we need to sum up all I not equal j ei times ej and the expectation value, which we have here. And how many of these terms do we have? Let's write this here again. It's n plus, and then essentially all these terms have the same absolute value 2q minus 1, and there are exactly n times n minus 1 terms in the sum here, because I should not be equal j, and the value is 2q minus 1 squared. So times 2q minus 1 squared. So that's the expression for the second moment. But now when you look at this, so you see there is a term proportional to n and a term proportional to n squared. So, oh wow, so this means we don't actually have a power law here. So what happened? So if we look at in a log-log scale, log n, and here we plot log of the second moment of x here, then we see here a function which goes proportional n plus a term which goes proportional n squared. So this means we have a function which starts in the log-log plot with our slope 1, and then for large time goes with slope 2. Or, oops, here, sorry, I was getting a bit out of the window. So if you look at the second moment in the log-log plot, we start to grow with slope 1, and then we have slope 2. Or if we would have taken the square root, we would have started with slope 0.5. So we would have started with a random walk, with a diffusive behavior. But for longer times, if we take the square root, we have a displacement which goes then proportional to time. Yeah, so if we take the square root, we don't have this increase with slope 2, but then only increase with slope 1. So we start diffusive, but then there is a transition to ballistic motion. How can we explain this? And that's clear. If we have this random walk which is biased, for small times we don't see the bias yet, so we have really something which grows the distance from 0 grows just diffusive as a square root of time, so that's this point. But if we wait long enough, then we really see the bias here. So on average the walker will always follow the blue line, and this means after a long time we really see this ballistic movement. We see that the square of the distance goes quadratic with time, or the square root of this, so the distance goes linear with time. So we have a transition from the diffusive to ballistic motion. So it would be actually here we would have here diffusive, and then later in long time we have ballistic, because the bias starts to play a role. Now you could say, oh, where is our universality gone, because now we don't have this diffusive behavior. And then that's the trick. When we have a biased random walk, the mean square deviation we cannot take as simple as this. We really have to look for the variance of our distribution here. So let's plot the calculate the variance of the distribution. So what is the variance of x? So that's the second moment minus the first moment squared. So we have here the second moment. We have n plus n squared times 2q minus 1 squared minus n 2q minus 1 squared. And now we take the first moment squared minus 2q minus 1 squared n squared. And then you see these quadratic terms cancel, meaning this all the terms in the ballistic term cancel, because we now subtract this mean value, and we are left with something which just goes proportional to n. This is 1 minus 2q minus 1 squared times n. And this here we have seen before. This was the variance of our increments. So the variance of the increments times n. And here we have again our diffusive behavior. The variance even of the biased walk goes proportional to time, which means the standard deviation of the biased walk is equals the standard deviation of the increments times the square root of time. So then we have it again, the standard deviation of x equals the standard deviation of the increments times the square root of n. And then we see, oh wow, everything is okay. We have again diffusive behavior. So this means if we want to calculate mean square displacement, and we are not sure here if we have a biased walk or not, we have always to calculate these here. We have to really calculate the deviation from the mean, so we have really to calculate the variance. And only if we have a biased walk we can forget about this. And if we do this correct and calculate the variance, then we see we still have diffusion, And so the scattering around the blue curve here, around the mean, just follows diffusion. Yeah? But if we instead would have just calculated the second moment, we would have seen a transition from a diffusive to a ballistic movement. Yeah? So, and then very often, if now we have a biased random walk, yeah, then we always go in a coordinate frame which goes with the center of gravity, so to say, and then we have only fluctuations around the bias, and so very often we don't have to calculate the variance, and it's enough to calculate only the second moment. Yeah? So we have fluctuations around the ballistic moving center. Yeah? So we can say it like this. So we have fluctuations around ballistic moving center. Oh, yeah, fluctuations around the ballistic moving center, and if we calculate the variance, then we see, yeah, it's just really diffusion. So that was an exercise for biased random walk. I hope I don't bore you with this, but I wanted to show you that we can, if we calculate all properties of the increments, then we can calculate all properties of the walker. It's a straightforward calculation. And so this was now still a process without memory. Yeah, so like we don't have memory in the system. And in the next video, I will take a random walk which is very, very similar to this, and you will see it when I show it. But instead of a bias, we do a short-term memory in the system. So then we want to know what's happening if we have again Bernoulli trials, but with a short-term memory, so that there is really autocovariance at later times. And what does this mean for our mean squared displacement? And do we still end up in a diffusive movement if we have memory? But so for this video, this is getting too long, so I will show you this in the next video. For the moment, thank you.